afternoon, everyone. Welcome to the class of CE331 Environmental Engineering 1 lab. So, today we will perform the test to determine the chemical oxygen demand that we call COD in water. So, let's start from the beginning. This concept is very important for you to know.
Sir, sound
Yes.
কম আসতেছে।
Okay. I think I can solve it now.
Yes, sir.
Okay. So, if you have a glass of water and you put organic matter here, organic matter, for example, it can be of various type. There are lots of organic matter in our surroundings. Organic matter, okay. Now, by the way, what is organic matter? Compounds with long chain of carbon hydrogen, right? It can be of different types. This is organic matter. It can be um, it can be the peel of a banana or any rotten food or any food maybe, uh, any rotten tree or any parts of a tree, any food that you consume, right? That's organic matter. Now, when you throw this in water, then what happens? Organic matter. Let's call it OM. This, okay? Shortly call it organic matter. Now, when you put this in water, this organic matter in water, you have microorganisms here, right? Microorganisms like in a pond, for example, you have bacteria, you have um, protozoa, you have what like many zooplankton and many other parasites and these things. So there are different microorganisms, micro scale. So these microorganisms actually, these microorganisms eat this organic matter. They take it as a food. This organic matter is a food to the microorganisms. How they eat this? They, this organic matter, right? They, in the presence of oxygen, they break them down and is outside the university. I cannot admit. So this is food. So these microorganisms take this organic matter as food, and in the presence of oxygen, they break it down. Initially, what is organic matter? As I told you, this is actually carbon, hydrogen, long chain of carbon, hydrogen, right? Right. So these microorganisms actually take them as a food and oxidize them in the presence of oxygen, and simply and make and break these chemical bonds and make it and transform it to more simple form like carbon dioxide. So only carbon and oxygen. So you detach them by microorganisms. So you get carbon dioxide, water, and carbon dioxide, water, and different gas. and other compounds. So we call it other compounds. Other compounds plus new cell. New cell means what? New cell means these microorganisms eat them and as a food, and they produce more microorganisms. They produce more microorganisms that we are calling new cell. Plus, they get energy from here, right? Are you following me, guys?
Yes, sir.
Yes,
Yes,
sir.
sir.
So, since you are doing this using microorganisms, and these microorganisms are biotic, basically, they are biotic means it's an adjective term, whichever has life, biotic. So and this is called degradation. So this process through which you degrade organic matter using microorganisms, that's called biodegradation. That this process is called biodegradation because you are causing this degradation. You are causing this degradation by using microorganisms. That's why it's biodegradation. Is it clear? Okay. Is it clear, guys?
Yes,
Yes,
sir.
sir.
Now, this whole process is happening where? In water. Remember, this is happening in water. Where is this oxygen coming from? This oxygen is coming from the dissolved oxygen in water. So this oxygen is actually coming from the oxygen which is dissolved in your water. That means with increasing reaction like this or increasing biodegradation, your consumption of DO is increasing. That means your DO is reducing because you are using more and more DO here. Therefore, you are losing your DO from water. Am I right?
Yes, sir.
That means in this process, your DO increases of water, increases or decreases with this process as you go from left to right. The DO of water increases or decreases. You are using it, so you are decreasing or increasing it. You are spending your oxygen here, right? Is it decreasing or increasing?
Increasing.
Huh? Decreasing or increasing? Say it again.
Increasing.
Increasing or huh?
Yes, sir.
I cannot hear you. Anyway, so here it will increasing. So if you had 100 BDT and you are spending from here, like you are buying something with 10 taka and 20 taka, is it increasing or decreasing?
Decreasing.
So why you are telling it's increasing here?
Or decreasing.
So your DO here is decreasing, which is bad for your water, which is bad for your water. So in terms of water quality, that means in a pond, if you throw organic matter like garbage, your food garbage and these things, then your DO will decrease. and therefore the fish and other aquatic environment cannot survive. If it go, remember DO, if it goes below 4 milligram per liter, then majority of the species may not be able to survive. Aquatic species may not be able to survive and they will die. Okay, so that's the problem. So you don't throw this organic matter into your water. Okay, let's come back to the organic matter again. So this organic matter, uh, how you can measure it, this types of organic matter, you can measure it uh, using the amount of oxygen used here. Higher is the organic matter, higher is the amount of oxygen used or consumed by the microorganisms. Again, higher is the organic matter, higher is the oxygen consumed by the microorganisms. So this oxygen is in fact a measure of how much organic matter, that means the pollutants present in your water body, in a pond or any other sources of water. So here, um, remember that this oxygen is a measure of how much organic matter is present in water. That means uh, this is called, and this organic matter is degradable by the microorganisms. This organic matter is degradable by the microorganisms. Now there are, if you go to organic matter, there are two types of organic matter. One is that biodegradable. That means this is biodegradable. That means they can be degraded by the microorganisms. They can be degraded by the microorganisms. Number two, non-biodegradable. That means they cannot be degraded by bacteria and virus. For example, in case of biodegradable organic matter, for example, if you put a mango here, mango, with time, this mango will rotten, right? Right or wrong? Initially, if it's green, then it will ripe, and then eventually with time it will be rotten, right? Right or wrong?
Yes, sir.
That means this is biodegradable, and rotting down, that what does that mean? That's basically biodegradation by microorganisms. So microorganisms are actually degrading them. Why do you put your food in refrigeration? Because you decrease the temperature so that the microorganism cannot work in lower temperature. That's how you save your food from rotting down. Okay. Anyway, so that's an example, right? Mango. This is an example of biodegradable organic matter. Biodegradable organic matter. This is of course an organic matter. What is non-biodegradable matter? Let's think about sugar. If you do you need to preserve or refrigerate your sugar to keep it well? Huh? Do you need to refrigerate your sugar to keep it well?
No, sir.
No, sir.
Why? Because microorganisms cannot break them, microorganisms. That's why this is non-biodegradable. So that means if it's sugar, then microorganisms cannot break them. But if it's a mango, then microorganism can break it down. So there are two types of organic matter. One is biodegradable, and the another is non-biodegradable. So if you call it biodegradable, and you call it biodegradable, you call it non-biodegradable. So total organic matter is what? Equals to biodegradable organic matter and non-biodegradable organic matter. Am I right? Hmm? Okay. Now, if you measure this oxygen from this biodegradation of microorganisms, then which type of biodegradable organic matter you will find? This one or this one? Number one or number two?
Sir, বুঝি নাই question টা, sir.
Okay, let's explain the process. For example, come here. If you measure the oxygen, that will eventually give you an idea of how much organic matter is present here. Because as I told you that higher is the amount of oxygen, higher is the amount of higher is the amount of organic matter, then higher is the amount of oxygen. So if you measure this oxygen, then you can get an idea or quantify the amount of organic matter. So, you know, if you have a glass of water which has organic matter here, which has organic matter, and at time t equal to 0, you measure, let's do it here. At time t equal to 0, you measure your oxygen, dissolved oxygen, okay? You measure your dissolved oxygen. At time t equal to 0, for example, um, at initial condition, there was no organic matter. There was no organic matter. So, for example, DO was healthy, the 8 milligram per liter. 8 milligram per liter at time t equals to 0. Now you add organic matter. What would happen? This will happen, right? Now microorganisms will degrade, will eat them, and will consume the water. Sorry, will consume the oxygen from water. That means after 1 hour, for example, hour. After 1 hour, you will see your DA will reduce, maybe 7. After 2 hours, after 3 hours, 4 hours, if you measure it, okay, you'll eventually found after maybe 48 hours, you'll eventually will see that the DO has reduced to maybe 2 milligram per liter or something like that. Are you following me?
Yes, sir.
Yes, sir.
Yes, sir. DO is reducing because this
Yes,
reaction is
sir.
happening. There is organic matter. Microorganisms are consuming organic matter and consuming oxygen to oxidize the organic matter. So, and then you see that it's not further after 5 days, for example, uh, 200 hours or something like that. Okay, so that you'll see that your DO is again maybe 2, so it's not further decreasing, so it has reduced a lot. You see the DO, it has reduced like this, and then it's not further decreasing. That means your oxygen, all, all the organic matter has been degraded and oxygen has been consumed. Now if you take the difference within this 2 minus 8 minus 2, you take the difference 8 minus 2, right? This is 6. This oxygen has been used to oxidize all the organic matter. Am I right or wrong?
Right, sir.
That means this demand, it was the demand of oxygen, right? This is the demand of oxygen. So oxygen demand. So this oxygen demand is actually telling you how much organic matter was present, how much organic matter was present in your water. Again, using oxygen demand, that means how much the oxygen has been reduced. Using that measurement, you can quantify how much organic matter is present in your water. So if I call this is oxygen demand, O D, oxygen demand. What does it represent? Yes, this is oxygen, but it represents what? Organic matter. Am I right?
Yes.
Okay.
Yes, sir.
Now, let's come to the point. In this reaction, microorganisms are degrading the organic matter. That means which type of organic matter is this? Is it biodegradable or non-biodegradable? If microorganism can degrade this, then is it biodegradable or non-biodegradable? If the microorganism can oxidize this organic matter, then is it biodegradable or non-biodegradable?
It's biodegradable.
Biodegradable. Biodegradable. That means bio, microorganisms can degrade it, so biodegradable. So from this reaction, if you calculate the oxygen demand, that will tell you the organic matter. What type of organic matter? Biodegradable organic matter. Biodegradable organic matter. Is it clear? Therefore, we call it biochemical oxygen demand. We call it biochemical oxygen demand. BOD. Okay. Biochemical oxygen demand. Clear?
Right.
So, if you involve the microorganisms in the reaction, in the degradation of the, or say it in other way, if the in the overall organic matter, in the overall organic matter, the portion which is biodegradable, that is biodegradable organic matter, we call it biodegradable organic matter. Let's BDOM, let's call it biodegradable organic matter. And what is non-biodegradable organic matter? Let's non-biodegradable organic matter. Okay, so let's clean this out. And so organic matter can be biodegradable organic matter plus non-biodegradable organic matter. This portion this portion is degradable by microorganisms. This portion is not degradable by microorganisms. Okay, so whatever that is degradable by microorganisms, we call it biodegradable organic matter. And we measure it with whom? Biochemical oxygen demand, BOD. Don't get confused with the name. Yes, it is biochemical oxygen demand. It's a measure of oxygen, but it represents organic matter. biodegradable organic matter, right? Right?
Yes, sir.
Okay. Now, how to calculate this portion? How to oxidize this portion? Bacteria cannot degrade them. Bacteria cannot oxidize them. Then how? You have chemical, a strong oxidizing agent, for example, potassium permanganate. These are a strong oxidizing agent, right? Strong oxidizing agent. They can oxidize this as well as this, both. So they can oxidize the total organic matter. So organic matter, potassium permanganate plus oxygen. This is degradation of all types of organic matter. So the oxygen demand from there, the oxygen demand you get from there, this is what? You have used a chemical, that's chemical oxygen demand, and it has oxidized all type of organic matter, both biodegradable and non-biodegradable. This is a total organic matter. So this is the total organic matter. So we, and since we have used chemical oxygen demand, so we call it COD, chemical oxygen demand. And this chemical oxygen demand is basically the total one. This chemical, this COD, this COD is basically the total organic matter. That means you can write that COD, that means the total organic matter, equals to biochemical oxygen, biodegradable organic matter, that is BOD, plus non biodegradable or non um, let's call it non COD plus BOD plus, so this is basically total organic matter. BOD is the biodegradable organic matter, plus you can call it NBOM, for example, non biodegradable organic matter. Non biodegradable organic matter. Is it clear up to this, guys?
Yes, sir.
So, in a nutshell, you have organic matter. This is two type: biodegradable organic matter, non-biodegradable. Biodegradable organic matter, non-biodegradable organic matter. It can be represented as COD. It can be represented as BOD, and this is whatever it is. And it can always calculate by COD minus BOD. That is non-biodegradable organic matter, right? COD minus BOD is this, right? So these two terminology is incredibly important to understand their mechanism and what they really mean. This is very important to, incredibly important to know. Okay, is it clear? This COD and BOD. COD is all type of organic matter. COD represents all all types of organic matter, and BOD represents only biodegradable organic matter. All types means both biodegradable and non-biodegradable. Is it clear?
Yes,
Hmm?
sir.
Okay. Now, so COD is basically BOD plus non-biodegradable organic matter. Now tell me which one is larger, COD or BOD? Or at least equal. Which one is larger, COD or BOD? From this equation, cannot you say if NBOD is always positive, it cannot be negative, then which one is larger, COD or BOD?
So COD.
COD. If NBOD is 0, then they might be equal, COD equals to BOD, but COD cannot be less than BOD. It can be greater than, COD can be, COD has to be greater than or equal BOD. Okay, so today we will learn how to determine COD. So determination of chemical oxygen demand. Okay, so read this very carefully. They have, this is the same thing whatever I told you so far. Now this is very important. What is the advantage and disadvantage of COD and BOD test? This is the reaction that you are using, that organic matter in COD we are using chemical agent. We are using a chemical agent. So organic matter plus oxidizing agent equals to carbon dioxide plus water. Okay. Like I said, potassium permanganate. Here, you don't need extra oxygen maybe here because you already have oxygen here. So potassium permanganate, that will oxidize this. Organic matter plus oxidizing agent equals to carbon dioxide plus water. Okay. Now, if you want to calculate BOD, here the bacteria takes at least 5 days to 5 days to degrade the organic matter. That means to determine BOD, you need to wait for 5 days. But COD, in case of COD, you are using chemical, right? So it can be done within a few hours. So this is an advantage of COD test over BOD test. In case of BOD, you need 5 days. In case of COD, you need a few hours. You can, to get the COD test, you need to wait a few hours, and to get a BOD test, you have to get the result of the BOD test, you need to wait for 5 days. But COD test also has some disadvantage. The disadvantage is what? That if you only calculate COD, you'll never get an idea how much of the organic matter is present in the water that is biodegradable. That's the problem. To know how much of the water is biodegradable, you need to determine BOD. Okay? So that's the advantage and disadvantage of BOD test. Very important for your exam. Read this very carefully. Okay? COD values are greater than BOD values or equal, especially when biological resistant organisms difference. Okay? So, oh, by the way, why did you say 5 days? Usually, if you look at this graph, Where? Which graph? This graph. Remember this graph? This graph. If I draw it here again, DO value reduces, and this curve gets flattened. How much day? After how much day? After 5 days. After 5 days, the curves get flattened, and after that you don't need to measure the value, because after this may be 2 or 2, 2, 2, or 1, 1, 1, 1, anything. So it does not decrease further. So this bacteria takes 5 days. These microorganisms take 5 days to oxidize the organic matter. Are you following me?
Yes, sir.
And after that, this is negligible after 5 days. So usually we measure, I would not say 100% is achieved, rather 95% or more than that. So that's well enough for us. So if in case of BOD we measure up to 5 days, so therefore we call it 5-day BOD. We call it 5-day BOD. Clear? Clear.
जी सर
5 days. Okay. Environmental significance. This is it has a massive environmental significance. COD is often measured as a rapid indicator of organic pollutant in a river. If you go to a river and you want to see how much polluted the river is, then BOD and COD, these two parameters are incredibly important to know. It is normally measured in both municipal and industrial wastewater treatment plants and gives an indication of the efficiency of the, you know, if you have a treatment plant here, if you have an industry here, you cannot directly discharge the water after processing, because this water is wastewater. So you have to install a treatment plant before you discharge them in the water. So this treatment plant, the objective of the treatment plant is to reduce this BOD, COD, and as well as other pollutants. Now, this treatment plant, is it working properly? To check this, whether this treatment plant is working well and efficiently, you need to collect the sample from here, collect the sample from the treatment plant. We call it effluent treatment plant, ETP. We collect the sample from here, and then we measure BOD, COD to check whether this is being reduced or not. You collect the sample from here before ETP and after ETP, and you measure the BOD, COD and you compare them. You measure BOD, COD here, you measure BOD, COD here, and you compare them. And also you check the standard. Bangladesh Environmental Conservation Rule, they have a guideline that limits the industry owners or industries how much BOD they can discharge in the water. Okay, is it clear? What is the limit? According to Bangladesh Environmental Conservation Rule, drinking water standard for chemical oxygen demand is 4 milligram per liter. It cannot go beyond 4 milligram per liter. For wastewater effluent, allowable concentration of CBOD varies from 200 to 400 milligram per liter. What is CBOD, by the way? BOD is of again two types. The CBOD and NBOD. So this is this is organic matter with carbonaceous without nitrogen, and this is organic matter with nitrogen. Is it clear?
Yes, sir.
Okay. So that's why they are calling it CBOD. Now, for example, I want to give you an example which will hopefully make it crystal clear for you. For example, this is a textile industry. Textile industry, and they take water and then you use it in the processing of textile, and then after the processing they have the wastewater. This wastewater has COD very high, maybe 800 or 1000 milligram per liter. But if you want to discharge this water into a river, can you discharge it? What is the limit? 200 to 400. You cannot discharge it. So you have to install a treatment plant. This is effluent from the industry, from the textile industry. This is an effluent. Okay, this is effluent. EFFLEUNT, effluent. So we need a treatment plant, which is called effluent treatment plant. This is called ETP. Did you hear the name ETP? Tannery industries has been transferred majority from the Hazaribagh area to Savar, and then you need effluent treatment plant (ETP) to treat the water. Right? There are frequent news, a myriad of news about this ETP in this kind regarding these kinds of industries. Did you hear this ETP, this terminology?
Yes,
Uh, So this is ETP. So the purpose of the ETP is to reduce the treat the water to reduce the COD below 200 to 400. For example, it will reduce it to 150 milligram per liter, and then this water can be discharged into the water. Clear? So this 800 milligram per liter COD has been reduced here up to what? 150. 150. Clear?
yes, sir.
जी सर.
Okay, what we're gonna do here, um, so what we are gonna do here, we are gonna determine COD, right? So how we are gonna do it is very easy. Organic matter, we have organic matter, we will use potassium permanganate, and we will do titration. Okay, we will do titration. And while we do titration, we need to know the end point of the titration by using an indicator, right? Right. What indicator we are using here? Ammonium oxalate. By the way, this potassium permanganate is pink color. Okay, this is pink color. So potassium permanganate. You can also use potassium dichromate. You can also use potassium dichromate. This is basically yellowish color, I believe. But here we will use potassium permanganate. Some people may also use this color. Okay, so potassium permanganate. So yeah, so they attack the carbonaceous and not the nitrogenous matter. So this way we will be calculating CBOD. Sorry, the chemical oxygen demand, but without nitrogenous matter. Anyway, so this is we are using a strong oxidizing agent. That's why they will oxidize almost all organic matter. Therefore, it will be COD, chemical oxygen demand. We are using a chemical. So we need. So the procedure is this. First of all, in the 100 milliliter beaker, 250 milliliter Erlenmeyer flask, okay, you take 100 ml of the sample for which you need to determine the COD. So you take 100 ml sample of sample. Okay. Now in an Erlenmeyer flask, now add 10 ml of dilute sulfuric acid. This is to uh, to expedite the reaction rate. So 10 ml of dilute, okay, it's not uh, concentrated, dilute sulfuric acid. So diluted sulfuric acid and 10 ml of standard potassium permanganate solution. 10 ml, 10 ml KMnO4. Okay, 10 ml KMnO4. Heat the flask. Why do you need to heat it? Because this oxidation process is expedited by the heat. So you heat this. You heat this. Okay. Heat the flask in a boiling water bath exactly 30 minutes. Keeping the water in the bath above in a boiling water. By the way, you don't directly heat it. You put it in a mm, bowl of water, and now you heat this. So the water will be heated, and then your flask will also be heated. Exactly 30 minutes. The heating enhances the rate of oxidation. As I told you, the heating enhances or expedites the rate of oxidation reaction in the flask. Okay. If the solution becomes faintly colored, that means color gets away almost. That means faintly, the color fades away. That means the most of the potassium permanganate has been utilized in the oxidation of organic matter. And in such case, the repeat above using a smaller sample. Okay, we will come to this point later. For example, we have added 10 ml potassium permanganate. We have heated the sample, and and after 30 minutes, add 10 ml of standard ammonium oxide. What happens here? You have to understand this. Yeah. Let's, for example, you had um, you had 8 milligram per liter, 8 milligram per liter COD in the water. Here, guys, are you following me?
Yes,
Yes,
sir.
sir.
Sir,
Milligram per liter. Okay. To balance 8 milligram per liter of COD, you needed, for example, maybe mm, let's call it equivalent for now. For example, 8 ml of KMnO4. Let's call it equivalent. By the way, you don't know this COD amount. You need to know this. You don't know this amount. Okay. So to oxidize this 8 milligram per liter COD, you needed 10 milliliter potassium permanganate. Fine. How much remaining, guys? This is used. How much is remaining, guys? Huh? 10 minus 8. equals to 2. Am I right or wrong?
Yes.
Okay. So you do not have COD. Do you have COD now? Right now you do not have COD because already this 8 ml potassium permanganate has oxidized this COD. So you don't have COD anymore. What do you have? You have this remaining 2 milligram, 2 ml potassium permanganate. 2 ml potassium permanganate. Clear?
Yes.
What do you have in this solution now? Only 2 ml potassium permanganate. You do not have COD. Okay. Now let's come to another topic. This potassium permanganate, this is an oxidizing agent. Oxidizing agent. Oxidant. There is another thing, ammonium oxalate. Ammonium oxalate. Ammonium oxalate. Ammonium oxalate. Ammonium oxalate. This is exactly opposite this. This is reducing agent. This is oxidizing agent and this is reducing agent. So if you mix them, they cancels each other. Is it clear?
Yes, sir.
Okay. Now you take them a concentration in such a way so that 1 ml potassium permanganate can oxidize 1 ml ammonium oxalate. Clear? 1 ml potassium permanganate can oxidize 1 ml so ammonium oxalate. Okay. Now let's come back to the point here. What do you have here? 2 ml potassium permanganate, right? Hmm?
Yes, sir.
Okay. What is the color, guys, of potassium permanganate? Pink. So therefore, since you have potassium permanganate in the water, so the color is still pink. Why? Because you have potassium permanganate here. Right or wrong? The color is still pink. How much potassium permanganate you have? 2 ml. Now, if you add 10 ml of ammonium oxalate, now you add 10 ml of ammonium oxalate. 10 ml ammonium oxalate here. What would happen? 10 ml ammonium oxalate. Let's do it here. 10 ml ammonium oxalate. How much potassium permanganate remaining, guys?
2 ml.
2 ml. Okay. So who will win? Ammonium oxalate will win. So from 2 ml of ammonium oxalate will cancel 2 ml of potassium permanganate. I would say balance potassium 2 ml potassium permanganate. Am I right? So remaining of ammonium oxalate AO is what? 10 minus 2 equals to 8. Am I right or wrong?
Right.
Do you have a potassium permanganate here? 2 ml? No, because this has been cancelled by ammonium oxalate. What do you have now? You have 8 ml of ammonium oxalate. This is actually similar to the amount of COD. You need these actually. If you can calculate this, you can calculate this. How you calculate this? Oh, by the way, whenever these 2 ml from out of 10 ml ammonium oxalate has oxidized 2 ml of potassium permanganate, is the is there any else potassium permanganate available? No, right?
Yes, ma'am.
That means there is no potassium permanganate now. That means the pink color will go away. So the pink color will go away, and you will have only 8 milliliter of ammonium oxalate. So in this solution right now, you have only 8 ml of you have only 8 ml of ammonium oxalate, and this is colorless because you do not have potassium permanganate now. Okay, fine. So in this stage, we have 8 ml of ammonium oxalate. How do you calculate this? You use a burette, and from the burette you titrate it with potassium permanganate. You titrate this, and it's colorless. All on a sudden, if you continue adding potassium permanganate, all on a sudden you will see that pink color comes again. That means all the 8 ml of ammonium oxalate has been oxidized by potassium permanganate, and the reading from here you get, which is equal to there, right? The reading from this potassium permanganate you get, that is actually equivalent to this 8 ml of ammonium oxalate, right or wrong? So these you got 8 from here, and that's basically your COD. Okay,
Yes, ma'am.
okay. So that's actually easy. So instead of potassium permanganate, you can also use any other oxidizing agent here. Okay. So how do you determine COD equals to milliliter of potassium permanganate used in step 6? That means step 6 means this step. Which step? This step. How much you needed? 8. How much you needed? 8. So 8, let's put it 8 here, milliliter, 8 ml, and then 100 divided by milliliter of sample used. How much sample you have used, guys? You have used how much sample? Remember? 100 ml. 100 ml. So you put 100 here. So your calculation COD will be in this case 8 into 100 divided by 100, right? Divided by 100. That's it. 8 milligram per liter. Is it clear?
Yes, ma'am.
Fine. Now we skipped a topic here. Remember? What did they mean here? The thing is, uh, where? Here, yeah. For example, you had higher COD, more pollutant water. For example, 25 or 15 milligram per liter COD instead of 8. Now, if you add 10 ml of potassium permanganate, would there be any potassium permanganate remaining? No, because this is 15. Already all the potassium permanganate has been consumed by this COD. Now you have excess 5 milligram per liter COD maybe. You don't have potassium permanganate. Am I right or wrong? Are you following me? Huh?
Yes, sir.
Yes,
Okay.
sir.
So if you see that after addition of 10 ml of potassium permanganate at the very beginning, that this color, pink color, goes away. That means your strength of COD is very high. Then what you do? You dilute your sample. You dilute your sample, and then you do the test again. If you dilute it 5 times, then whatever you get um, from this experiment, for example, you diluted it for 3 times, 3 times diluted it. one third. Okay, and then whatever you get, you'll get what? You'll get 5. After the test in this air here, you will get, instead of 8, you will get 5. And how much it was diluted? 3. So multiply it with 3, so it will be 15, which is the actual value. Clear? Is it clear?
Yes, sir.
Yes, sir.
So that's it. That's all about the test, I believe. This concept of COD BOD is very important. I'm telling you again. So make sure you understand these things very well for your exam and also for your professional life. Okay, in near future, if you go for any professional exam as well as professional practices, you need this. Professional exam means any type of exam, higher study or BCS, anything. You need these things to know very well. Okay. So biochemical oxygen demand, that's basically the bio that represents the biodegradable organic matter, and chemical oxygen demand that represents the majority, almost all kinds of organic matter, both biodegradable and non-biodegradable. Okay, so I think that's all from this lecture. Do you have any questions, guys? You have any questions?
No, sir.
No
No,
questions.
sir.
Okay, then thank you very much for attending the class. Have a good one and stay safe.